Welcome to our channel. Today we're diving into the mysterious and fascinating world of black holes. Imagine a place in space where gravity is so strong, so utterly dominant, that nothing, not even light, can escape its grasp. These are black holes, cosmic monsters lurking in the darkness, shaping the fabric of space and time itself. So buckle up, fellow space explorers, as we embark on a thrilling adventure into the heart of the cosmic abyss. Let's start at the beginning. Not all stars fade away peacefully into the cosmic night. Some, the true titans of the cosmos, meet a far more dramatic end. These stellar behemoths, after burning through their nuclear fuel, reach a critical tipping point. The outward pressure from their nuclear fusion can no longer hold back the immense inward crush of their own gravity. The core collapses in on itself, an implosion of unimaginable scale. This core, once the heart of a star, becomes compressed to an infinitesimally small point, a singularity, the very essence of a black hole. The outer layers of the star, caught in the gravitational maelstrom, plunge inward, accelerating towards the newborn singularity. This infalling material, heated to unimaginable temperatures, releases a final, brilliant burst of energy, a supernova, visible across the vast expanse of the cosmos. And at the heart of this cosmic explosion, hidden from view, lies the newly formed black hole. Now, imagine approaching a black hole. As you get closer, the pull of gravity increases, pulling more strongly on your feet than your head. This is the tidal force, stretching you out like cosmic spaghetti. Fun, right? But let's say you could withstand the spaghettification. You'd eventually reach a point of no return, a boundary in space-time known as the event horizon. Picture a sphere around the black hole. Cross that sphere, and you're gone forever. Not even light, the fastest thing in the universe, can escape the gravitational clutches of a black hole once it crosses that boundary. The event horizon is a cosmic trapdoor. Once you cross it, there's no coming back. Objects appear to slow down as they approach the event horizon, their light stretched and distorted, frozen in time on the very edge of forever. Black holes, despite their name, aren't just empty voids in space. They're actually some of the most massive objects in the universe. And how do they get so big? They eat. Imagine a cosmic buffet with a black hole at the center. Anything that wanders too close, be it gas, dust, or even entire stars, gets caught in its gravitational web. This material, spiraling inward towards the event horizon, forms a swirling disk of superheated gas and dust called an accretion disk. This disk, glowing brightly with X-rays and other forms of radiation, can be millions of degrees Celsius, hotter than the surface of our sun. And as the black hole devours more and more matter, its mass, and thus its gravitational pull, grows stronger, allowing it to capture even more material from its surroundings. Chapter 4. A Cosmic Waltz. When black holes collide. Now, imagine two black holes, locked in a gravitational dance, spiraling closer and closer to each other. These cosmic partners, their fates intertwined, are destined for a spectacular collision. As they draw nearer, the fabric of space-time itself becomes distorted, sending out ripples, gravitational waves, that propagate across the universe at the speed of light. These waves, predicted by Einstein over a century ago, were only recently detected, ushering in a new era of astronomy. The two black holes merge, forming a single, more massive black hole. This event releases an unimaginable amount of energy, more than the combined output of all the stars in the observable universe. Chapter 5. Time warps and reality bends. The curious case of time dilation. Let's talk about time travel, or at least the closest thing we know of, time dilation. You see, time isn't absolute, it's relative. It can be affected by gravity. The stronger the gravitational pull, the slower time flows. And near a black hole, where gravity is king, time plays some truly mind-bending tricks. Imagine you could observe a clock falling into a black hole. As it gets closer to the event horizon, you'd notice something strange. The clock would appear to tick slower and slower, its light stretched and redshifted by the intense gravity. From your perspective, time for the clock would seem to almost stop as it reaches the event horizon. But for the clock itself, time would continue to flow normally. It wouldn't even realize anything was different. If you could survive a trip near one, you'd age slower relative to everyone else on Earth. Chapter 6. Beacons in the Darkness. The X-ray glare of black holes. Black holes, despite their name, aren't entirely invisible. While they don't emit light themselves, the material swirling around them in the accretion disk can shine brightly, particularly in X-ray wavelengths. As matter falls into a black hole, it gets heated to millions of degrees, releasing a torrent of X-rays. It's like a cosmic spotlight, illuminating the black hole's location. These X-ray emissions are so powerful that they can be detected by telescopes here on Earth, providing us with a way to study these enigmatic objects. Many of the black holes we've discovered were found by observing these telltale X-ray signatures. Chapter 7. Spinning into the Void. The whirling world of rotating black holes. Hold on to your hats, folks, because black holes can spin, and when they do, they don't just spin like a top. They drag space-time itself along for the ride. This phenomenon, known as frame dragging, is one of the most bizarre predictions of Einstein's theory of general relativity. Imagine stirring a cup of coffee. The swirling liquid drags the coffee beans along with it. Similarly, a rotating black hole twists space-time around it, forcing everything in its vicinity to rotate along with it, like a cosmic whirlpool. This swirling space-time even affects the shape of the black hole itself, distorting it from a perfect sphere. Rotating black holes, also known as Kerr black holes, have two event horizons, an inner and an outer, and a region called the ergosphere, where space-time itself is dragged along with the black hole's rotation. Chapter 8. A Cosmic Zoo. From stellar remnants to supermassive giants. Black holes come in different sizes. Think of it like a cosmic zoo, with a whole range of these fascinating objects on display. The smallest are stellar mass black holes, formed from the collapse of massive stars. These are the most common type of black hole, and they typically have masses a few times that of our Sun. Then there are the intermediate mass black holes, a bit of a mystery, as we haven't observed many of them directly. They bridge the gap between stellar mass and supermassive black holes. And then, we have the true titans of the cosmos, the supermassive black holes, found at the centers of most galaxies, including our own Milky Way, with masses millions or even billions of times that of our Sun. Chapter 9. Galactic Architects, Shaping the Cosmic Web. Supermassive black holes, those lurking behemoths at the hearts of galaxies, aren't just passive bystanders in the cosmic drama. They play a crucial role in the formation and evolution of galaxies themselves. As material falls into the supermassive black hole at its center, it releases vast amounts of energy, heating up the surrounding gas and driving powerful outflows. These outflows, like cosmic winds, can regulate star formation, preventing the galaxy from collapsing too quickly and influencing the overall structure of the galaxy. Supermassive black holes are like cosmic gardeners, shaping the distribution of stars and gas within their host galaxies. Chapter 10. The Quantum Paradox. Black holes aren't entirely black. Black holes, those cosmic vacuum cleaners, might not be as permanent as we once thought. Enter the mind of Stephen Hawking, who proposed that black holes actually evaporate over time, slowly but surely, through a quantum process known as Hawking radiation. At the event horizon, quantum fluctuations can create pairs of virtual particles, one with positive energy and one with negative energy. Near a black hole, the negative energy particle can fall in, while the positive energy particle escapes as Hawking radiation. This radiation, carrying away a tiny bit of the black hole's mass energy, slowly causes the black hole to shrink over time. Don't worry though, the evaporation process is incredibly slow. A typical black hole would take longer than the current age of the universe to completely evaporate. Journey's End, or is it just the beginning? Thanks for watching. If you enjoyed learning about black holes, don't forget to like, subscribe, and hit the bell icon for more fascinating science content. From collapsing stars to time warps and quantum paradoxes, black holes push the boundaries of our understanding of the universe. So, keep exploring, stay curious, and never stop asking questions about the cosmos. See you next time.